Dear students, today we will talk about Llyods single mirror. It's an experimental arrangement which uses a single mirror, a single light source, and a screen to produce the interference pattern. So, the experimental arrangement is like this: you have a single light source here, you have a plane mirror here. So, this is the silvered surface of the mirror, and this is its reflecting surface. This is the single light source. Here we have the screen. Now, let us first decide that what will be the region on the screen within which we will find the interference pattern, that is within which we will find the bright and dark fringes. Of course, we will not be obtaining that pattern on the entire screen, but within a certain range, and that range will be determined by the end points of the mirror. How? Suppose this is the incident ray at one end point. It gets reflected and meets the screen at this position, for example. There is another ray from the source which hits the screen directly, producing an interference pattern here. It can be constructive or destructive, we don't know. Now, another extreme would be that a ray of light hits this end and it gets reflected at this point. Then there is also a direct ray which meets the point here. So, the interference pattern will be obtained between these 2 points, A and B only, not beyond, not before, right? Of course, there will also be reflections from the intermediate region, but we are determining the extreme A and B. There will also be interference patterns in between, right? But we are determining the ends only. Now, if we drag these lines, extend them backwards, these lines, reflected lines, here and here, they meet at certain point. Remember, it should be a straight line meeting somewhere, right? So this is another source, S2, virtual image. It is the virtual image of S1. So we have obtained two sources now. S1, its virtual image S2, which are coherent sources, and they are going to produce an interference pattern that will be visible on the screen. We have also determined by the pattern of reflection that what will be the range within which we will obtain the interference pattern. Now, if you recall Young's double slit experiment, this apparatus, this arrangement looks more or less like that. We have two slits S1 and S2 there. Similarly, we have two sources S1 and S2 here. Suppose they are separated by certain distance d, right? What was the condition of maxima and minima there? What was the path difference? It was xd by d. The path difference between the two rays from two slits was xd by d. For constructive interference, we would equate it with n lambda. And for destructive interference, we would equate it with 2n minus 1 lambda by 2. But here the condition is reversed. This is the condition for minima and this is the condition for maxima. And why does that happen? Because on account of reflection from a denser to rarer medium, there is an extra path difference of lambda by 2 or a phase difference of pi that is introduced in the light wave. You have already done that in the previous video wherein you learnt in detail about Stokes relations. There you have learnt that on account of reflection from a denser to a rarer medium, a path length, a path difference of lambda by 2 or a phase difference of pi is introduced. On account of this reason, the conditions for maxima and minima in case of Llyods interference pattern gets reversed. So xd by d is n lambda, this is the condition for minima, and xd by d is 2n minus 1 lambda by 2, this is the condition for maxima. Let us try to understand that a bit more. See, for instance, if you recall the Young's double slit experiment, you have a ray of light coming from screen, this slit 1, another ray coming from slit S2 meeting at certain point and producing interference pattern. What was the path difference? It was this much, isn't it? This path difference was actually going to determine whether the interference at this point would be constructive or destructive. Now, if d was the distance between the two slits and theta is the angle, and we know that we have drawn a perpendicular on this ray of light, right? Then this extra path that is covered by the wave coming from slit S2 is obviously equal to d sine theta. This is what we had calculated over there, d sine theta. Now, d sine theta was directly put equal to n lambda for case of maxima. But in this case, since on account of reflection, a phase difference of pi or a path difference of lambda by 2 is also introduced, this equation gets modified by d sine theta plus lambda by 2 is equal to n lambda. So that when you take this lambda by 2 on this side, this gives n minus half lambda, right? So this is 2n minus 1 lambda by 2. This is how the condition gets reversed from n lambda to 2n minus 1 lambda by 2, right? So we are obtaining interference pattern, bright and dark fringes on the screen. And moreover, remember one thing, if C is the central position between the two slits S1 and S2, rather two sources S1 and S2, this central position is going to be dark because there is no reflection at this point. By virtue of the diagram, we can understand that there is no reflection at the point C, due to which this is a dark spot. So that's all about Lloyd's single mirror apparatus.